Hi class. In the last video, I did an example of a power series solution to a first order equation. So it was a little bit simpler. I'm going to do an example now of a second order equation. So this is example 4 in the book. I started it in class, and now I'm going to do all the details in this video. So here's the equation. We've got 1 plus x squared times y double prime minus y prime plus y equals 0. So the gist here is that we want to do a power series expansion around an ordinary point x equals 0. And how is it obvious that x equals 0 is an ordinary point? So remember, an ordinary point means that when we have our equation written in the standard form, that our p and q equal to 0. So in standard form, or I don't even know if it's exactly called its standard form, but whatever, we want to get the y double prime by itself, so we'll divide by 1 plus x squared. And we get y double prime minus 1 over 1 plus x squared y prime plus 1 over 1 plus x squared y equals 0. So our p of x is negative 1 over 1 plus x squared, and q of x equals 1 over 1 plus x squared. So both of these, both p and q, are analytic at x equals 0. Because analytic functions, remember, are functions that you can represent as a power series, and that includes all of our polynomials, all of our sine functions, and all of our rational functions, as long as the denominator is not equal to 0. But if you plug in x equals to 0, you get 1 into the denominator. So both p and q are analytic, therefore we know we can do a power series expansion at this point. Okay? Okay, so the gist here is that because we have ordinary points, because we're worried about an ordinary point, which we're going to guess that our solution is in the form of a power series. So we have y of x equals sum from n equals 0 to infinity, a n x to the n. And so this is a power series that's centered at 0, which is why we don't have x minus x naught to the n. That's sort of the standard form for our power series, but x naught equals 0. So that's why we have it looking like this. And then we can also take our derivatives. So y prime of x equals, the first term of our power series is constant. So when we take the derivative, it goes away. So we start from n equals 1 to infinity of n a n x to the n minus 1. And our y double prime of x is equal to the sum from n equals 2 to infinity of n minus 1 a n x to the n minus 2. And so now we'll just plug in to our equation. We've got our y prime, and our y double prime. And we get 1 plus x squared times our power series for y double prime. And okay, I'll just write it all out now. So we have this whole equation that all these power series equal to 0. And what do we really want to do? Well, we want to, this is our solution, our y. And it's all determined for us. We know it has the form of this power series, but we need to find the an, okay? So that's our goal. Now, the strategy to do that is if we can combine this into one power series, And if we do that, we can use the fact that we know about power series to say that sum from n equals 0 to infinity of an x minus x naught to the n equals 0 implies if and only if an equals 0 for all n. So if we can combine everything on the left-hand side of our equation into one power series, then set the coefficients equal to 0. And that'll give us some relationships, some equations that we can use to solve for the an. Okay, so that's what we have to do. So the next thing we have to do now is combine everything on our left-hand side into one power series. So let's move it up here. Now, furthermore, the strategy to do that is that we want to make everything look like we can't really add these together straight away because we've got like an x to the n and then an x to the n minus 1 and everything is a little bit off. So we're going to just like rejigger things so they all look like x to the k, like some stuff times x to the k. Then we can combine them. Okay, so we're going to do this one at a time. First, this term here, this first term, this is actually two terms. We have 1 times the power series plus x squared times the power series. So first, I'm going to worry about 1 times power series here. So that's going to equal just power series by itself, n equals 2 n minus 1 an x to the n minus 2. Okay, so I want to have an x to the k, so I'm going to do a change of variables here. I'm going to set k, just write down what you want to happen. So I want k to replace n minus 2. So now think about other places where you have n's, and what do they have to look like in k, in terms of k? So that means that n is going to equal, we have an n in a couple places, n is going to equal k plus 2. We have an n minus 1, and so that equals k plus 1. And we need to replace the limits of our integration, so that's when n equals 2, that corresponds with k equals 0. K equals 0. And then we don't really have to write this, but n equals infinity corresponds with k equals infinity, so that infinity will stay the same. So this sum we can rewrite as k equals 0 to infinity of k plus 2, k plus 1, a k plus 2 x to the k. All right. So that's our first term. Next let's do the x squared times everything. I'll move over here just to be a little efficient with space. So we have x squared sum n equals 2 to infinity n minus 1 a n x the n minus 2. So again, well, okay, actually before I do that, I can put this x inside the sum. So that's equal to the sum from n equals 2 to infinity and n minus 1 a n x to the n, because I can, if I multiply every single term in my power series by x squared, I increase the exponent by 2 each time. So now this is super easy because I have an x to the n here. I want it to look like x to the k, so all I do is do k equals n. And so that's equivalent to k equals 2 to infinity k minus 1 a k x to the k. Because remember, k is just a dummy variable that only exists within the sum, just like the integrating variable in an integral. All right, let's do this one now. So we have our, n, sum from n equals 1 to infinity, n a n x to the n minus 1. So it's basically the same thing we did before, but now we're going to set k equal to n minus 1, then n equals k plus 1, and when n equals 1, that corresponds with k equals 0. So this sum is going to equal k equals 0 to infinity of k plus 1, a k plus 1, x to the k. Now you'll notice that our starting limit is 0 here, it's 2 here, and it's 0 here. These don't need to match. The important thing is that the exponents on the k match. All right, so then our last one is easy. We're just going to swap out k for n. So our last one is k, or n equals 0 to infinity, a n x to the n equals the sum from k equals 0 to infinity a k x to the k. So we are now going to add up, instead of the 4 we have here, we're going to have this, the blue, plus the green, plus the red, plus the yellow. Okay, so I don't know where to move this. I'll rewrite it and then I'll move everything away. So now our equation becomes I'll just rewrite everything: blue plus green plus red plus yellow. And of course we can actually combine them, and that's exactly what we needed to do. So now the only issue is that some of our sums do look different, because some start at 0 and that one starts at 2. So we'll just start writing out the terms a little bit separately. So let's first write out, all right, I'm gonna, I guess, use blue here. So when k equals 0, let's write out the k equals 0 term. We can plug into the blue one and we get 2 times 1 of a2. So 2a2, and then x to the 0 is just 1. We don't get anything from the green term. When we plug into the red term, k equals 0, we get 1 times a1, so plus a1. And then in the yellow term, we plug in k equals 0 and we get a0, so plus a0. So that's k equals 0 is all of that stuff right there. Now we also need to plug in k equals 1, so let's do k equals 1. But I'm still going to write it in black. So we get a plus. K equals 1 from the blue term, we get 3 times 2, so 6. A of 3, a3, and then x, plus, still nothing from the green term, but from the red term we get minus 2 a 2 x, and then from the yellow term we get plus a1 x. Okay, so that's all the k equals 1 terms. And lastly, now we can combine everything else together. and then I'll simplify a little bit more. So now we have all the terms from k equals 2 on. So we get the blue ones, k plus 2, k plus 1, a, k plus 2, x to the k. I guess I could have still been color coding this, but I didn't. So then k minus 1, ak, ak x to the k minus k plus 1 ak plus 1 x to the k plus a k x to the k equals 0. And then the sum is around all of this stuff in brackets. So let's simplify this now. And we get a bunch of terms without any x's. So 2a2 plus a1 plus a0 plus a bunch of terms in front of an x. So 6a3 minus 2a2 plus a1 x plus, now we can pull the xk, x to the k, and we'll just go and correct that right there, out of everything in the brackets there. So we get the sum from k equals 2 to infinity, brackets, k plus 2, k plus 1, a, k plus 2, plus k minus 1, a, k, minus, shrink this down, k plus 1, a, k plus 1 plus a, k, bracket, all times x to the k. And this all equals 0. So that means that we can set all the coefficients equal to 0. So this equals 0. This equals 0. And all the stuff in brackets equals 0. So that gives us the relations that we need to figure out what the a's are. Okay, so now I can go through and correct some of my mistakes. I think I only see one at this point, but that should just be a minus 2a2 minus a1 because the a1 came from that red sum over there as a negative. Now, this is one of the more complicated examples. Some of the other examples in the book and that we may see in class or in the last video, you can actually get like a nice tight expression for things. And this is not one of those. So we're just going to sort of plug in and figure out a couple terms. So first, from the yellow equivalents, we can get that 2a2 minus a1 plus a0 equals 0. We can solve for a2 in terms of a1 and a0. a1 minus a0 over 2. And we can't really, we're not necessarily going to be able to solve for a1 and a0. Those are going to be like kind of our constants. And we expect, because this is the second order equation, we expect to have some constants. And so we will see these in our in all of our answers. Everything is going to be sort of in terms of a1 and a0. So that's okay. But now that we have a2, we can use the green one to say we've got 6a3 minus 2a2 plus a1 equals 0. And then that tells us that a3 equals 2a2 minus a1 over 6, which equals 2a2 would just be a1 minus a0 minus a1 over 6, which equals negative a0 over 6. Okay, so that's a little tidy at least. So next we have the blue equation there. All the stuff in the blue brace equals 0. And that'll give us the higher order k term. So let's think about what it means just when, well, let's see, there's a couple of different ways you can do it. We can do it sort of arbitrarily. So we could do it for k, we can get a k plus 2, and we want to get that alone in terms of all the other ones. So if we kind of simplify things down, we end up getting this, which I'll write out. And that relationship holds for any k greater than or equal to 2. Which makes sense because the first one we would get would be a k plus 2 for, if k was 2, then you'd get a4. So we've already got a2 and a3, and now we can get a4. So let's try a4. So we plug in k equals to 2, and that gives us 3a3 minus 4 minus 2 plus 1 is 3a2 over 4 times 3 is 12. So that's a3 minus a2 over 4. Now we have a2 and we have a3, and so we can plug those in, and I'm just gonna, I'm not gonna do all the arithmetic out, you can verify it. 2a0 minus 3a1 over 24. And you can keep going. It's a giant pain, right? And they do this out in the book a bit, and I'm just going to write a5 so you can see a5 equals to 3a0 minus a1 over 40, etc. And so this is gross, but like it's the answer that we need, okay? So in the end, remember what the thing we're looking for, y of x equals the sum from n equals 0 to infinity a n x to the n. Well, we can start writing this out, right? So that equals a0 plus a1x plus, now we know a2, it's this, x squared plus, or minus, a0 over 6x cubed plus, blah, we had all that stuff. Now, we still have like all these a1s and a0s all mixed together, so we can actually pull the a0s out and pull the a1s out separately, and we get a0 times 1 minus 1/2 x squared minus 1/6 x cubed plus etc., plus all the a1 terms. We get a1 times x plus 1/2 x squared minus, if I had written out the other one, it would be like the next one would be 1/40 x the 5th, etc. So you can see this is just like the solutions that we saw in chapter 4. We have like one constant times y1 and a constant times y2. Okay, so this has, that's why it makes sense for these a0 and a1 to be left as constants. All right, so that's section 8.3. There are some, you might want to read through some of the examples in the chapter to see how they like find more closed formed solutions to things. But this is like sort of the long and tedious way to do it.